We've done a lot of really interesting work on our vacuum tube computer up to this point. We've built a proof of concept, we completely redesigned the result register, and we even built 2 operational amplifiers to be used as Schmitt triggers to create a clock that will hopefully synchronize all of the different aspects of the machine. And a slight tangent about those operational amplifiers, and that is using 6 vacuum tubes to create an operational amplifier to be used as a Schmitt trigger is incredibly inefficient. There's actually better ways to build Schmitt triggers. And so in the future, we'll probably take a look at the clock again and change out the operational amplifiers for some proper Schmitt triggers. Now, I built those 2 operational amplifiers, and I have them sitting on boards, and I have an idea for another project that will use both of those. So we're going to get into that in a future episode. But for this episode, I want to take a look at the vacuum tube computer as a whole, because what I want to do is build something that's going to be used in the finalized version of the machine. Everything we've built up to now has been testing theories or building concepts, but I want to build a part that's actually going to be in the machine, in the finished version. And so that's what we're going to do today. And the part that I want to build is the instruction register. So let's hop over to the bench. We'll take a look at the plan, how we're going to build the instruction register, and then hopefully we'll hop out to the garage and fire up the mill. So let's get started. So here's the block diagram for the MC14500 that we're trying to replicate. And the part that I want to build today is the instruction register, which is just this little block right down here. And this may seem like it's a pretty small chunk of the overall design, but the instruction register itself actually has 4 D flip-flops in it. So for example, the IEN register uses just a single D flip-flop, and that's this box up here. And you can see that the result register is a single D flip-flop and the OAN register is a D flip-flop. So that's 1, 2, 3. That's still less than the number of D flip-flops that's used in the instruction register down here. So if it was all drawn to scale, the instruction register would be huge. And it is one of the most tube-intensive parts of the build. But it's a fairly simple design. It's just 4 D flip-flops. And D flip-flops are something that we've experimented with before. We've built a couple D flip-flops. So let's take a look at the schematic that we're going to use to build the D flip-flops for this instruction register. So this is our edge-triggered D flip-flop design. It uses 6 NOR gates, and we spent an entire episode building and testing one of these. So if you're interested in learning more about how exactly this D flip-flop operates, I definitely recommend going to check out that previous episode. But in short, we've got essentially an SR flip-flop over here on the right, and then the set or reset pins are activated by the collection of NOR gates over here that are arranged in a pretty unique manner. Now the clock has an inverter on it. Because the clock is such a massive portion of the entire machine, I'm going to deal with how to integrate the clock properly in the future, which I'm sure future me will be very upset at past me for, but that's a problem for him and not me. But because we've built this particular D flip-flop before, we already have a good vacuum tube design for it. Now it looks a little intense because there's wires heading in every single direction, but it's really just 6 NOR gates, and one of the NOR gates has 3 inputs and the rest only have 2 inputs. And so you can see our clock comes in down here as well as our data, and then we have our output and our inverted output. And this is important. We're going to need both of these outputs for future parts of the build. Now, compared to what we built in the previous D flip-flop episode, there have been a few changes, and they're actually based on the new inverter testing that we did just a couple episodes back. And so that is that all of the NOR gates now have 33,000 ohm resistors on the plate. And to go along with that, the voltage divider resistors coming into the grid are now 220,000 ohms each. Also, even though it's not shown here, I've added desensitizing capacitors to the grid point of each of these tubes. And that's actually to really help prevent the problem of racing from occurring, which is where the flip-flop will flip multiple times during a clock pulse. Now that's not going to be such a huge problem for the instruction register, but if the instruction changes at an inopportune time, it could potentially cause a wrong instruction to be input. Also, I really want to build these D flip-flops into a module that can be used in multiple places. So I want the D flip-flop to be as universal as possible. So to that end, I spent some time in DesignSpark PCB, my favorite EDA software out there, and I designed a board with 6 tubes on it that would be our D flip-flop module, and that's what you can see right here. So we've got a design that I'm pretty happy with, so now I think it's time that we head out to the garage and build one of these. And here is the finished result. I am just so happy with the way that this turned out. It's such a compact design. I mean, it's as compact as you can get with vacuum tubes. I mean, you could probably fit 1,000 transistors in the same space that I fit 6 vacuum tubes. But it's compact for what it is. So we've got our clock and data pins right here. And I've got a third pin down here for reset that will reset the D flip-flop to 0. And then over here on the right, we've got our output and our inverted output. And then these 3 pins at the top on both sides are kind of like a power bus that runs from left to right. So we've got negative 12 volts, 24 volts, and then ground. And so this is a power bus that spans across the entire board. And so this can be chained together with other boards to make it easy to distribute power across the entire machine. So the smart thing now would be to plug this into a breadboard and test it out, but I'm feeling a little spicy, and I think it's just going to be a lot easier to test all 4 of them at once. Nothing can go wrong with that, right? But there's one more thing that we got to think about before we get too far into this. And to fully understand what that is, we need to take a look at the gate level representation of the entire processor that we're trying to build. Now, just looking at it like this, that is a whole lot to take in. But we're only really concerned with this bit right here on the left. These are the 4 D flip-flops for our instruction register. Now, the part that is concerning me is the decoder next to it. So we need to take that 4-bit address and turn it into 16 individual signals. And that's what this massive collection of NOR gates here on the right is. And so each output and inverted output needs to feed several NOR gates. And so since the output is feeding multiple inputs, we need to start thinking about a problem called fan-out. So to fully understand what fan-out is, we need to take a look at what exactly we're asking of our inverter. And so here on the left, we've got our triode and we've got a 33,000 ohm plate resistor up here. And then the output is coming off of the plate directly. Now, with only 24 volts being supplied to the plate, the amount of current that can be supplied out of this output is incredibly limited. And then we can imagine each of these resistor networks over here being the resistor divider network that goes into the grid of another inverter. But each one of these is going to negative 12 volts. So that's actually from plus 24 to minus 12. That's a 36 volt drop across there. And so each one of these 220,000 ohms, even though they're big, is going to have a substantial draw on the output of our inverter. Now, we did some testing when we set up our set-reset flip-flops, and so that was one way to see what our inverter would be pulled down to with these large resistors here. And starting at 24 volts, we saw that it was dropping down to about 21 volts. And that was with only one other inverter input affecting the output. If we have to supply that output to multiple other inverter inputs, they're each going to impact the output, pulling the voltage down. And so when we get up to 2, 3, maybe even 4 different inputs coming off of that one output, it's going to pull the voltage so low that it no longer functions correctly. And this is what fan-out is. It's how many other inputs a single output can drive. And for our standard inverter, that's an incredibly low number. I wouldn't really want to drive more than maybe 2 or 3 inputs. And so what we need to do is we need to put something right here in between all of these inputs and the output to buffer it, to make that stronger. So how do we build a buffer using only vacuum tubes? Well, it turns out that's pretty easy to do. So on the left here, we have our standard inverting amplifier. And you can see we've got our 33,000 ohm plate resistor, and then the tube is connected up directly to ground. And you can see that we can get about 0.7 milliamps of power out of the plate here. Now on the right, we have something called a cathode follower. Now there's a couple massive differences between these two. The first is that the inverter inverts whatever the input is. So if we have a logic high coming into the grid, we get a logic low coming out of the plate. But a cathode follower doesn't invert. If we have a logic high coming into the grid, we get a high output. Now you'll also notice that there's no plate resistor drawn here. And you can put a plate resistor in that's incredibly small. I usually put in about a 100 ohm resistor, but you can actually build a cathode follower with no plate resistor whatsoever. And you'll see that our cathode is connected through a very large resistor to ground, and then the output is pulled directly off of the cathode. And so if the input signal increases, more electrons can flow, and the potential of this cathode becomes closer and closer to the potential of the plate. And that just so happens to be held at 24 volts. And so our output, which comes directly off of the cathode, is only being impeded by the internal resistance of the tube. And through some of our previous testing, we found out that for the 6AU6, the internal resistance is around 3,000 ohms, which means that our output will be able to supply 8 milliamps of power. That's more than 8 times as much power as our inverting amplifier over here. So we should be able to drive a huge number of other inputs without worrying about affecting the quality of that output signal. So we're going to need a cathode follower buffer for each output and inverted output of all 4 D flip-flops for our instruction register. So I spent quite a lot more time in DesignSpark PCB and I came up with this design, and I'm pretty happy with it. Now there is one extra addition, and that is that I want an indicator to see what is stored in each D flip-flop. And I'm going to do that with these really neat little vacuum fluorescent displays. So let's hop back out to the garage, fire up the mill again, cut out our new circuit boards, and then plug it all together and see what happens. Oh my God, it looks so cool. I can tell that as we build more and more of this machine, it's going to become harder and harder to fit it all in the frame of the camera. But as far as problems go, that's a pretty cool problem to have. So we have our 4 D flip-flops set up here, and then each one of these tubes here is a cathode follower buffer for the output and inverted output of the D flip-flop to the left of it. And then to the right of each one is a tiny little vacuum fluorescent display that works as an indicator to show us what value is stored in the D flip-flop. So if the indicator is on, that means that the D flip-flop is storing a 1, and if the indicator's off, it's storing a 0. And so this all comes together in this insane amalgamation of 32 vacuum tubes and 4 vacuum fluorescent displays of absolute madness. I love how this thing looks. Now you'll notice that I've got a collection of wires coming out of the side here, and this is to control it. These 3 wires on the top of each one are going to be the power bus, so that's negative 12 volts, 24 volts, and ground. And then the brown wire coming out of the bottom on each side is the clock, and that goes into a spare bus on the breadboard over here because the clocks are all going to be controlled at the exact same time. And then that's tied into a simple little push button on the breadboard over here. And that push button is set up so that it has a 10,000 ohm resistor to 24 volts so that the input into the clocks is high all the time. And then when I push the button, it pulls that low. So that's our inverted clock input. And then the remaining wire goes to these 4 individual toggle switches that allow me to set the data that will be stored in each D flip-flop. Now, right now the entire thing's off, so let's flip the switch and see what happens. All right, so there was a whole lot of really interesting stuff that just kicked off all at once right there. I don't know if you could see it, but because all of the vacuum tube heaters are running in series, each heater has a slightly different resistance when cold as opposed to hot, and it's going to vary from tube to tube. So certain heaters got a little more current than other heaters, and so we ended up with this really interesting pattern of heaters glowing up a little too bright, and then the other heaters warming up and bringing the resistances back down to equal. So it was this really kind of chaotic orange glow that spread across the entire machine. That was really cool to watch. And we also had our first indication that something good is happening here, that it's potentially working, because we saw some of the VFDs turn on and then dim out. And even this VFD here on the end turned on and stayed on. And so that meant that as the tubes were warming up, values were being stored or erased because it's all going to end up in a kind of chaotic state initially. So let's set all of our switches to 0 and toggle the clock and just reset everything to 0. Okay, that's good. It turned the one VFD that was still on off. So that's good. That means that this is working to some extent. We reset everything to 0 now. So let's go for broke. Let's set all 4 switches to 1. And when I set the switches, nothing should happen on the actual machine. So that's good. That means that whatever our input is, it's not affecting the D flip-flop or causing it to flip without the clock. And speaking of the clock, let's do it. Let's push the button and see what happens. Yes! Look at that. All 4 vacuum fluorescent displays kicked on at the exact same time. And now there's a 1 stored in all 4 locations of our instruction register. So let's do an interesting pattern. Let's do 1 0 1 0. Yeah, there we go. Okay, so we have 1 0 1 0. Now let's do 0 1 0 1. Yes. Oh man, that's all working amazingly. And so now if we just turn off this one here and get 0 0 0 1, that's a load instruction. So there we go. We have our first proper instruction stored in our instruction register. We just don't have anything to do with it yet. So next we need to build the decoder to separate that out into 16 individual steps. And that's going to need to be buffered as well. So this is starting to get huge. The scale of this thing is starting to set in. But the idea of building something that's going to be bigger than this table potentially is really cool, I think. So there we have it. We successfully built the instruction register. And this is the finalized instruction register that will be used in the actual finished product. So we've taken our first proper step towards completion. And I could not be happier with how it turned out. It looks amazing. It works phenomenally well. I am just over the moon. And now I'm really excited for building the next parts. But we'll save that for some future episodes. But in the meantime, I'm gonna keep punching in different instructions and storing them because I just think it's so cool to watch. So thank you guys so much for watching, and we'll see you in the next episode.